high-class algebra.
Great. So first of all, it's great to be here in this beautiful place. So thank you so much to the organizers for bringing us here and for inviting me to give a talk. So I'm going to talk about the paper which appeared 2 weeks ago. And it's called Symbol Alphabets and QCD and Flag Cluster Algebras. And this is the work done with Mark, who is here, our former postdoc, Andrzej Pokraka, who has just started his new 5-year position with Universe Plus, shared between University of Amsterdam and IS, and our current second-year graduate student, Hee-Cheng Wen. Okay, so, and simultaneously with our paper, there's been work of which we learned at CMSA school 3 weeks ago by James, Lara, and Omer, and the paper actually appeared this morning, so I didn't have a chance to compare, but they had a chance to compare. And I thought that would be, when I arrived, I heard that they're posting their paper, so we reorganized the schedule, and I think it would be nice to hear Omer, because they did more than us. They investigated adjacency, so Omer will talk about what I won't say in the next 30 minutes, right? Okay, so very good. So here's the outline of the talk. The talk will have 2 parts. I'll start with a review. I do realize that many of you heard from me for the past 10 years on this topic. But I will just have kind of minimalistic review of things we only need for the main statement. So it will be very, the explanation in the simple, I'll try to do it in the simplest possible terms. So I'll just remind you the connection between the symbol alphabet in n equals 4 Young-Mills theory and Grassmannian cluster algebras. And this observation goes back to over 10 years ago in our paper. And for the past 10 years, I've been working on n equals 4 Young-Mills, but I've been hanging out also with a lot of physicists. And I've been getting a little bit of critique on, all you do is these remarkable structures, but this is n equals 4. But now I'm very excited that cluster algebra made its way, and mathematical structures made its way to more physical theories such as QCD. So I'm super excited by this paper. So, all right, very good. And then Omer will continue on the subject. Okay, so very good. So I'll start with the main statement. So the theory, the quantum field theory that we're looking at is a planar n equals 4 Young-Mills theory. And the main statement is that the symbol alphabet for n-point amplitudes is described by the Grassmannian cluster algebras. And that's the statement that first was made in our paper with students Dan, John Goldin, Sasha Goncharov, and Christian Vergou, and Mark Stradlin. So here, I'd like to emphasize the following. So there's the left-hand side of this sentence and the right-hand side of the sentence. So there's a symbol alphabet for any n-point amplitude, which is left-hand side, which is physics statement. So somebody does physics calculations and obtains an answer to this question: what is the symbol alphabet for n-point amplitude? Then there's the right-hand side, which is mathematics. It's a very well-defined notion. What is the Grassmannian cluster algebra? So then one makes a comparison and observes the match or mismatch for other cases. I will elaborate on that. So that's the main statement. So I thought I will have maybe 3 slides on the left-hand side and right-hand side. So in particular, I'll start with 3 slides telling you, maybe aimed at younger folks, what the symbol alphabet for n-point amplitude is. And then I'll have 1 slide, which already we heard from Lara, on what Grassmannian cluster algebra is. And then I'll show you the evidence for the statement for the simplest case. Okay, very good. So refresher number 1, 2 refreshers. Left-hand side. Symbol alphabet for n-point amplitude. So amplitudes are indexed by 3 numbers. Number of points, helicity, which I will skip completely in this talk, and a loop order. So n and l are main numbers. And in principle, you can compute any amplitude by summing over all Feynman diagrams with n external edges and l internal loops, then integrating over the loops. It's very important that we are, in my talk, like many other talks, we're not talking about integrand, we're talking about the final integral. So Amplituhedron describes the integrand, but this is what you do after you integrate. Okay, so, and the simplest way to explain this is that what are the amplitudes? What are these amplitudes? They're some functions of a kinematics, okay? So what are the functions of? What is the kinematics? We heard this in a number of talks already. So the kinematics describing the amplitudes is given by those momentum twistors Z that we've seen that lie in the Grassmannian, and we're going to be using Pluka coordinates on CP3, where there's everywhere. We've seen this many times, and there are lots of experts in this, so I don't need to review this. So there'll be a lot of brackets, and the brackets are the corresponding determinants. So these are functions over kinematics. So what kind of functions? So the functions are different types of functions. So, and I will be focusing on just something called generalized polylog functions. So in this particular theory, it's important that we're talking about a plane n equals 4 Yang theory. The functions have at L loops, so you fix, remember, the L and N. At L loops, they have uniform transcendentality, in particular transcendentality 2L. For example, the simplest functions are Li 2L, which are polylogs. Then we will talk about generalized polylogs. They are defined here. But it's known that for higher N and L, more complicated functions start appearing, and these are called elliptic polylogs. So we have a nice white paper a couple of years ago with a lot of, 20 authors, I think, on that paper, reviewing the current then status of the elliptic polylogs. But that became just studying those functions, it became a little subfield of amplitudes. They have even their own amplitudes annual meeting. But I'm not going to talk about that. I'll just restrict to generalized polylogs. So for these types of functions, it's very useful to define an object called symbol, and that was first applied to physics in a paper from 15 years ago. So that's, most of you have of course seen this, but if you haven't, so to define a symbol, first you write this uniform transcendentality functions as certain recursion, and then you define the symbol recursively by this formula. So for example, for log x, the symbol is x. For Li2, the symbol is minus 1 minus x times x. And then the arguments that appear in a symbol are called letters. So we'll be talking about collectively about those letters, and we call this symbol alphabet. Let me just review. We talk about amplitudes as functions on the kinematics, but functions are these polylogs, and we kind of apply the symbol operation, and we end up talking about these letters. So that's the data that we would be discussing that comes from physics. Now, I should also emphasize that this data is hard to obtain. There's been a lot of work obtaining this data. I don't have more to say about it. And so the results of the papers that I will be talking about comes from the new results, which were mostly obtained by Hen's group and people around them, that they've been doing for the past 10 years, obtaining those symbol letters for various theories. So I just want to advertise the meeting that we're going to have. So it's been 15 years since the symbol. And we will have, in December, this meeting, covering all the great advances in this field. Okay, so very good. So that was physics. We will be talking about symbol alphabet of endpoint amplitudes, and this comes from a certain calculation, very hard calculations in physics. Then the math. So already it has been reviewed, so I won't say it again. So what we're talking about is Grassmannian cluster algebra. So that's to define the cluster algebra, you need two things. You need initial seed and mutation. So the initial seed for Grassmannian GR for n looks like this, and depending on the variables, you have the mutation rule. So again, I try to do that in the simplest possible way, such that I can show the slides to a junior undergraduate student and have them code and do something. So this is the flavor of my talk. Just so I know they're maybe not mathematician friendly, but it's undergraduate, junior friendly. So after you show this to a junior undergraduate and mutation rule, they can code and produce cluster variables. So it took me a while. It took us a while. I should say it, I think I told Doran several times. But I actually learned first about cluster algebra. So Sasha, we were working in Sasha Goncharov was telling us that the letters that people were getting from physics have something to do with cluster algebra. We had no idea what it is. So then finally we sat down and learned what cluster algebra is. And actually the first clearest paper was actually Lawrence single author paper because it had A2, and once I understood A2, I could understand the rest. So, but the standard reference, of course, Lara already presented is the original papers by Fomin and Zelevinsky, and especially the recent book Torpere. Okay, very good. Okay, now I've explained left-hand side and right-hand side of the statement. So you have symbol alphabet in physics for endpoint amplitude, and it's described, which somebody computes. And then, on the other hand, you have cluster variables from Grassmannian cluster algebra, and they match. So right-hand side equal to left-hand side. And let me show you some evidence for this statement. So again, I apologize for the ancient work here, but yeah, the first time this was observed for 2 loops, 6 and 7 point amplitudes in our paper. So first, physicists have to do the calculation. So here you see the alpha. So this is the reason. Of course, for mathematicians, they see this, they immediately think cluster algebras, but we didn't because we didn't know what cluster algebra is at that time. And so the result of hard physics calculation is this formula for the letters. It's not explained, I realized, the brackets. Maybe on the next, actually I removed brackets are not explained, but maybe, yeah, somehow that, yeah, so these are some quadratic relations in brackets. Somehow disappeared from my slide. Okay, but anyway, so somebody meaning us and also Simon Caron-Hort for 7 points did the hard calculations, and well, our calculation was based on somebody else's even harder calculations, and got these letters for 6 and 7 points at 2 loops. Okay, and so then that's a physics result. The left-hand side, and now we compare it to the right-hand side. So to do this, you start with the quiver for GR for 6. You start with initial seed, do mutations, get your cluster variables, and that's exactly the 6-point alphabet. And you do the same for 7. That's the initial seed. You do the mutations, and then you get your cluster variables, and exactly you get the match. Okay. 2 slides on high L and N. Okay, so now that's a very nice example, but it's been around for over 10 years. So what's up here? So based on the fact that only cluster variables appear for 6 and 7 points, Dixon and collaborators, and this involves also significantly James and Omer, and I refer you to this nice review. They were able to compute to go higher loops. And of course, I'm sure from Lance's talks, they were able to compute 6 and 7 amplitudes to 8 and 4 loops. It's very important that they start with the alphabet of just these cluster variables, then they assume various physical conditions, find unique solutions, and I didn't specify all the details, but for high L now, I think this is the highest loop ever, probably the actual computation for the actual amplitude. So it's very, very impressive work. For high N, so far I told you about 6 and 7. So if you go to 8, so GR for 8 becomes relevant. So then the cluster algebra is infinite. So what do you do? But of course in amplitudes, there's a finite subset appears. That's point number 1. And point number 2 is that some of Songhee's students worked out the actual alphabet for 8 and 9 point amplitude. So again, it's a very, very hard calculations. And some symbol letters not cluster coordinates, they involve some square roots when you write it in terms of Kluckers. And there's been a lot of slow but consistent set of progress in the past maybe 5 or 6 years trying to understand those letters for 8 points and 9 points. So I normally have a list of all the papers, but I will just tell you my favorite one, which comes from actually Omer and James. So how do you get those square roots? So there are various approaches, which I'm not summarizing, but the simplest perhaps is, I don't know if you agree, but perhaps is this one, is that the infinite cluster variables of GR48 arise from quivers that have a double arrow like this. And so if you look at the cluster algebras given by this quiver, it goes forever. but it's been known, I hope that the reference is correct. It's been known since, maybe there's a previous reference. So it's been known that the square roots appear along this infinite mutation sequence as this limit. So there's a way in mathematics to obtain the square roots. This is just a statement. So James Omer, James's former student, Jack Forster, and actually my very first PhD student, who I'm proud of, Chris Calusius, applied this idea to actually GR48 and GR49, and were able to get those square roots. So I'm mentioning this because I'm going to be repeating this for the new theory. Okay, very good. So I finished this. So now we basically repeat, now part 2, we're going to repeat the same story for a different theory. And we will see, so very exciting, to me it's super exciting because I got a lot of critique for n=4 from lots of physicists, including that there are no scattering amplitudes in n=4. What are you doing? But mass disk QCDs and integrals, nobody will object. That's a useful, very important object in physics, and so I'm very, very happy about this. And the relevant cluster algebras, the candidate cluster algebra would be that of flat cluster algebra that we heard a very nice talk by Laura already. So I won't have too much to review. So now, second part. But you remember again, left-hand side, right-hand side. So we have flat cluster algebra, we can produce the letters, and we have simple alphabet that I will say a few words about. And then we try to match. So that's a very simple idea. Okay, very good. So before I tell about the more recent work, there's been actually in the past 5 years, there's been some of the previous nice papers, two very nice papers, trying to apply cluster algebras for just Feynman integrals. So everything in my first part of the talk was plain n=4. So now there have been 2 papers, one by Chicherin and Papathanassiou, and then later, more recently last summer, is by Papathanassiou and his student, Alish, and they found cluster algebra structure in Feynman integrals. So what they did is that they looked at this Feynman integral, which are drawn here, and these integrals have, so this is boldface, I don't know if you can see, this like is supposed to be massive. So 1 loop, 2 loops is an integral corresponding to this. So you take this integral, you do this integral, you take symbol alphabet, and you get certain letters. And remarkably, the letters are given by A2, C2, and G2 cluster algebras. So first, the most complete, so if we just start with this case, the symbol alphabet for these integrals up to 3 loop, the most recent one, has been worked out by Hen and collaborators. So again, I should say that Hen and collaborators for the past 10 years have been working hard on producing data. So again, none of this would have been possible without these very hard explicit calculations. Nothing, I can analyze mathematical structure as much as I want, but somebody had to do the hard work. And so they have the answer for the alphabet, and here it is. So now, it turns out that if you take the statements, so the first paper with Chicherin goes to 2 loops, but so I'll just go to 3 loops right away. So the relevant cluster algebra is for 1, 2, and 3 loops, A2, C2, G2. You start with an initial seed of 2 nodes, and you do the mutation. That's the mutation rule. So you recognize the A2 for L=1. It's quite remarkable. For L=2, is C2, and then for L=3, it's G2. So it will be interesting, of course, to get some data for higher loops and see what the pattern is. And you get, so from mathematics, you will obtain these cluster variables, 5, 6, and 8 cluster variables. Okay, so you know what these are. And on one hand, so that's right-hand side, and on the left-hand side, you have, as I said here, you have the symbol alphabet that they worked out. So then, what you do is you compare, and actually this is the change of variables that I've written. I didn't really define it, but for physicists they know what S, T, and P's are. But these are the objects that appear in the integral. So that's the change. Yeah.
It's clear what happens next. It's just it's a rank 2 cluster algebra series.
From mathematics, it's clear. Yes. Okay. So I think it's clear what happens in mathematics. Yeah. But somebody has to do the for loop. So I think it would be remarkable if somebody does the for. So hence and 30 people who work for him should hopefully with him in his group. I think hopefully will tell us. Yeah. So exactly. Yeah. So it would be very, very nice. Yeah. Okay, so very good. So now what's next? So that's 4-point with one massive leg. So I advertised, so the two cases that we'll talk about is 2-loop 6-point and 2-loop 5 points. So for the, let's start with 5 points, that's the easiest. So we, so again, the full, so again, these are 2-loop 5-point massless QCD. So different theory from, I'm omitting all the details, but we don't need the details. We can just open and be like engineers, open the paper and try to extract the answer. We cannot go through the details and everything, but the full alphabet has been worked out, planar and non-planar for these integrals, and the reference is these papers. And so I tried to write down the alphabet here. So for planar case, there are 35 plus 1 letters. For non-planar, there are extra 5 letters, which are written in red. So I didn't do all the details, just to give you a flavor that you can open these papers, you can get the alphabet. Okay? So then how do I explain the structure of this alphabet? So first, the letters were shown to coincide with those from a construction based on D4 cluster algebra. So this is based on the paper by Lara and James and Rose Glue. Okay? So, but this is not what I'm going to be doing. Instead, I will be utilizing the flags. You heard about everything about, you need to know about flag manifolds from, and their cluster algebras from Lara, so I'm not going to review. So what we will need to do is we're going to focus on 5 and 6 points, and only these particular flags we need. Okay? So this partial variety cluster algebra that you've seen from Lara, F2 n minus 2n, is embedded in this. So these are the two candidates to describe this alphabet that we will look for. Okay, so I'm very happy that I don't need to do this. So this was already introduced by Lara, the flag cluster algebra, so I will just skip right there. And the map between the variables and the corresponding objects, everything has been already introduced. So what I will need is just this picture. So now you, after Lara's talk, you're all experts. So if you take F235 cluster algebra, the initial quiver looks like this. And you, once you have this, you, undergraduate, can produce 22 cluster algebras, right, by mutations and everything. So that's what we need. So these are the D. So in this case, there's an isomorphism between D4 and GR36. So that these are the variables. So this is right-hand side. Now let's compare that with what we need. So we have on one hand in mathematics we have this for the candidate, and then we have this for the physics. So then we compare. So we compare, and it's a simple exercise. It turns out that the set that you get, the 22, is not closed on the natural group of on the natural cyclic group. So we need to take a union under the cyclic permutations, and then because you could say for cluster algebra I got only 22, right? But I had 25 plus 5 variables for physics side, right? So the counting. Yeah. So remember for planar young meals for 6 and 7 we had 15 and 49 and they matched, right? But here you saw, right? Here you had 22 cluster variables, but here you will be like, okay, what are you talking about? Because the counting doesn't work. There's 25 plus 5. So, but it turns out you need to do a cyclic permutation, and then you can get all of them. Okay, so that's 5 points, except for one letter, and this letter drops out of all known amplitudes in 4 dimensions. Yeah.
Go ahead, I'll ask you.
So for just the planar letters, if you write them in momentum twisters using infinity twister, is it some nice expression or not?
The letters or the... Yeah, you can write them, but yeah.
Does it make any sense kind of geometrically that involves the infinity twister?
I think the best geometry is, you can do better than this. So that, I think that's the variables and everything. See? We don't want momentum, we don't want infinity twisters, we want this linearity and that. So to me, it's a huge advantage to use their variables, yeah. You could do what you just said, but I think it's much nicer because this makes sense in mathematics, yeah.
Spoilers, you will get A4 cluster variables if you did not do that.
You could, yeah, but... Yeah.
So just a subtlety on this thing, though.
Yeah.
So actually you can see here, So your quadratic ones here.
You have quadratic
2, 3, 2, 3, 4, 5, 4, 5
Okay.
is actually a cyclic rotation of 1, 2, 1, 2, 3, 4, 3, 4.
Yes.
Shift by 1 unit. So if you only complete under cyclic, you won't get all 25 planar letters. You'll only get 20. And then you'll get the full non-planar if you complete under all permutations. But you won't get the full planar if you only complete under cyclic.
But are you saying that's not right, Steve?
So if you delete the things in the parentheses, I think 25 needs to become 20. But if you keep all permutations, it's still true that you get everything.
But I think, and I think we said all here.
Yeah, so
I think that's all right. Yeah. I think we need to take all. I think that's
it's just that the cyclic doesn't generate the full planar. That's all.
Okay. Let me double check. That is possible. I think that is possible. I got it right. Yeah, that's possible. Okay. Very good. So now, what about 6 points? So 5 minutes on 6 points. So that's the actual our main interest. So the full symbol alphabet for planar 2-loop 6-point integrals has been only worked out recently. So this is very fresh physics work. This is December and January of this year. So again, this was done simultaneously by this group. Most importantly, this is was explained to me, this is the thesis of Antonella Matijasik. So that was her thesis, and basically the main person on this work. I would just emphasize to all of you, please invite her to, if you want to hear more. So she's now she just graduated, but that's basically the result of her PhD dissertation. This very important result. So, but then good. So very good. So so the symbol has been worked out. I have the slide, but I skipped all the details, but I will maybe some, it's not fantastic, but to give you some idea. So the variables are the 9 variables, V's, and then we will use notations epsilon and delta, and you can open their paper, and some of my collaborators like to criticize the paper because they present 289 letters. I'm glad Johannes is not here, so I can speak freely. So they present 289 letters, but they're not all independent. So it's a basis, yes, output from Mathematica, I understand, but the number of independent letters is 245. Okay, so this is a list, and it goes like so the V variables I explained, and then there's things quadratic. So I kind of numbered them. I tried to extract the answer that is correct, yet it fits on one slide. So I put some work yesterday during coffee break into this. So they're linear. So it starts with W linear, and then it goes up to 48. At 49, they become quadratic. At 100, you can see how many of each type. They become cubic. Then there are letters. So these are kind of, I wrote a representative of each class. One representative of linear, one representative of quadratic, one representative of cubic. Then there are square roots of these. Then there are epsilons and delta, which I defined on the previous case. I can try to make this consistent. Then it's a V times epsilon. Then it's R plus V divided over R plus V, the structure. Then it's epsilon plus VV divided by epsilon plus VV. Then it's R epsilon plus W. W is defined here. So I try to make it like, it's kind of, might be a little bit hard. It takes some work to extract, but I try. Okay, so this is the answer from physics and hardcore calculation from Antonella's thesis, basically, and simultaneously paper by Abreu and collaborators. Okay, so now physics part, you have list. Now math part, you've seen this from Lara. This, you take this, exactly, you expert. Yeah, so you take the flag cluster algebra, this is the quiver, you have mutation rules, and you produce the list. Okay? And then you compare the list. So that's so there are various ways to summarize it, but that is a nice table that I just copied from our paper, that it turns out many variables are cluster variables, but there are unfortunately some that are not. So the result is as follows. So, okay, so there are 245 letters. The ones, okay, this is the line referring to the previous table, but there are 135 that are cluster variables. Then there are 40 that are algebraic, and we reproduce it exactly by repeating Omer's and James' exercise. So this again I should emphasize a very important work by our graduate student He-Chen Wen. Lots of work, but the method is that what I described. And then there are 7 that are analog of square root of delta that we don't expect to get, analog of 5 points. And then there are okay. So then you saw there's some that appear on line 4 that some are rational but are not cluster variables. So if we look at line 4 here, you see, so this we don't worry too much about because these only appear at order epsilon, so they don't appear in 4 dimensions. But there are 36 on line 2. Okay, now I'm going to do the counting. Line 2 and line 6. Line 2, okay, now that I have to do arithmetics. Line 2 and line 6, 36. So SHV is spin-Helicity variables, MV is Mandelstam variables. So there are these that, so the crosses that you might want to worry about is this and this. So these are somewhat mysterious and are not described by flag cluster algebra. Okay, so then what? Then we thought, okay, so maybe they would drop from the amplitudes. However, then we look at the paper by Johannes, Hen, Yang Zhang in May, and they do actually 24 of them do appear in the actual amplitude. Yeah, I have to again say there are a lot of papers by the Munich group, and it's hard sometimes a little bit to keep track. You have to, some of them on high page, but okay, that's we cannot just remove those letters from physical ground. Okay, yeah, that's the result. So we've explored so far the connection between the 245 symbol alphabets in planar massless 2-loop 6.5 integrals that has been recently computed in December, January, very recent work, and flag cluster algebras, which again, important work by Lara and Jianrong. Jianrong, I haven't mentioned also Lara. Jianrong's paper. So that's actually, of course, provided us the motivation to doing this, and that's what we find. So we have missing letters, and we're looking at them very hard. We have some conjectures that has something to do with C2 mutation. Maybe you guys have more to say about this. There's also a way, there are 2 groups, at least I heard at Amplitudes, have worked out, not from flags, but from GR49. They try to obtain, so one group by Song He, with various collaborators, and Yorgos Papathanassios' student actually told me he's also tried to, so the other exercise you can do, embed those letters in GR49, although it's not as, it's not a complete Rachmaninian, so there is some way to obtain them, and maybe that's interesting. Then, of course, one can go further, and okay, this so far I talked about the alphabet, but there's more due to again people, and this is what we hear from Omer about. That's the way I hope. So one can discuss the cluster adjacency of those letters. And Omer will, in today's paper, I think I have not yet looked. They didn't send me the draft. I don't know. So we did send them the draft. But yeah, so I will look at this today. But I think he will explain. So I'm very happy he agreed to talk instead of me. So he will talk about cluster adjacency of these letters. Very interesting. So then, of course, one can get. So there's been a whole program developing this further. They start with letters, but then you talk about adjacency. Then you talk about cluster functions. So all of that story now could be reworked for this case. And I think this Alan already mentioned, maybe Matteo will say, it would certainly be sort of nice work by the organizers on the Amplituhedron tilings for planar n equals 4. Certainly would be very nice to look at the tilings for momentum Amplituhedron and see if you can see flag cluster variables. So that's, I don't know if you're going to mention, but okay. Okay, and then finally, I think none of this is possible, this intersection between math and physics, without hard calculations. So somebody has to, I'm very happy, my new group, hopefully. But Yara is here, actually. So I think there's some tree loop data which leads, Yara joined also this now. I should hand also Yara now joined this. So there's some tree loop data available in this paper, which is recent. So the more data, the better for us. So we can go and explore the extra letters, what's happening, and consider. But it's very important to keep getting that data for physics.
If you see in the list of authors, Dima Chicherin, he's the one doing the hard calculation.
He's the one. Yeah, but you, yeah. Okay, so this you can say I have no knowledge, but okay. So anyway, there is data, and I think it's important to keep doing this. I hope you encourage production of even more. So yeah, with that I stop, and I think Omar hopefully will continue and tell more about adjacency.
So I know that this is probably not organized like that, the list of the letters, but is it possible to find some hierarchy starting from dual conformal invariant letters and then go like deeper in?
Yeah, we won't abandon dual conformal because you like dual conformal and it was 4. You want to start dual conformal and then go away from it, yeah?
Yeah, but start with the dual conformal and add more. Right? So
but
for example, there is something which would show up in n equals 1 super Young Mills.
But somebody should compute it.
And then there will be more letters for QCD.
Okay,
there
so
must
maybe
be
more
some
work
error.
for you to do n equals 1. Maybe tell Johannes. It's not let's go paper. I don't think. I agree. But it would be nice to do that. Yeah.
Well, there are 3 subalgebras inside these things.
But math is math side we can have undergrad, we can explain but the physics needs to be, so maybe, and go to n equals 1 by steps, could be. But I think the nice thing to me was not worrying. I heard so much criticism about n equals 4 in dual conformal. I mean, it's fantastic, it's great, but people always want more, they want more. So that's why I think that's why so nice Jiarong and Lara's flags,
I was wondering, how unique is the basis, or like, if you change the basis, can you get like?
I wish many authors, 10 people. I wish there would be discussion in the paper. You mean the basis of letters? How you do? I wish. I'm not going to be the one taking Johannes' papers and rewriting them in a pretty way.
I was wondering.
A lot of money, a lot of people, let them write it in nicest papers. I just take their answer.
I was just wondering.
I think that's a question for them.
How much freedom there is to move around, such that, I mean, is it like a no-go theorem that like the flag variety are not describing this, or maybe there is a better basis?
Better basis. I don't think there's a better basis to get into 36. I don't think that's possible. But a better, cleaner way, that is, maybe Omer.
So when you identify the letters in the alphabet and the flag, you don't find one-to-one correspondence. Letters in the 6 and 5 point amplitudes are products of cluster variables. So there's the basis if you're a cluster algebra fan.
It naturally wants to change the basis for you in some sense, but it's still not complete. So it's like a part of the basis.
But then, does it matter if you have the A or the X variables in the cluster algebra?
What is all A?
There are 2 types of cluster structure, like the A and the X.
We talk about A's.
Okay. Did you look at the X cluster algebra?
So even back in the days when we were doing this massage, X becomes, so first you do A, then X becomes important when you think about functions of cross ratios. So X's are cross ratios of A's, so that's natural, again, from physics. Again, that's the next step. Again, I think they write all the functions, and I think right, Yara maybe knows this much more. The functions are there also. So this was just alphabet, but maybe one starts exploring the functions, and then I think a lot of work has been done in 10 years for n equals 4. I think it's time to redo this.
Okay, I stop discussion now. We can still discuss in the afternoon.